Hi guys, welcome back to the 100 Days Machine Learning Crash Course. Today we are going to talk about decision theory. Okay, so far we have seen that probability theory gives us the framework to work with uncertain events and analyze the uncertain events. We want to make some decisions in the presence of uncertainty. So this is the target of decision theory analysis, that we want to make decision in the presence of uncertainty, and this happens a lot in pattern recognition problems. Okay, let's say x is the input vector, okay, is your input, and the target and the corresponding target for this input is t. So we know that the joint probability of x and t gives us the full information about the uncertainty in x and t, but typically we call the derivation of p of x and t, which is the joint probability, the inference, and typically it is so hard and difficult to obtain an expression for calculating the joint probability. Instead, in practice, we want to make some decisions based on the target values. In other words, we want to make some decisions based on which value of t is more likely to happen. Let me clear this with an example. Let's say you have an X-ray medical image. So when you have the image, means that you have a 2D thing. Maybe you vectorize it or not. If it is u int 8, means that it is unsigned int and 8 bits. Each pixel is between 0 and 255, right? So in this case, the pixel intensities, we call the value of each pixel intensity. So we put all of these pixel intensities in a vector. Okay, and the input of our model or anything, our input is x, which is which are the pixel intensities, and the t belongs to the class of this X-ray medical image, which we want to classify that if it is 0 means that somebody is normal, and if it is 1 means that somebody has cancer. So so we have an image and medical image, and from that we want to know somebody has cancer or not. So the probability, the joint probability of x and ck, we call the normal class C1 and call the cancer class C2. So the joint probability of x and ck gives us the full information about the class and the data, but what is important is p of the ck given x. What does it mean? It means that it is important to us that somebody has cancer or not, In other words, we want to know if we have a medical image X, what is the probability of somebody has cancer, somebody is normal or has cancer. When the probability of having cancer is more than the probability of being normal, we decide to take action of treatment, maybe for that patient, or gives him some pills or any other treatment. So what is important for our decision is to take somebody treatment or not based on the medical image. We just need to specify the conditional probability of CK given X. Means that what is the probability of, for example, if we derive this, means that what is the probability of somebody is normal. It is maybe C1 is better. Okay, somebody is normal given to his or her X-ray medical image. Okay, so although this is very informative, but this is enough for make the decision in this case. And for obtaining this, actually we could use Bayes' theorem. If you remember that, we could write this as follows. It is equal to P of X given CK times probability of CK over P of X. And P of CK means the prior probability, and it means that before we take the medical image, what is the probability of someone is in the class of normal or cancer. Okay, what is the probability? For example, if K is equal to 1, means that what is K is equal to 2, means that what is the probability of somebody has cancer, okay, in general, without looking at his or her medical image. Okay, and just note that if we have the joint probability, we can derive all of this value by marginalizing or conditioning this probability distribution. Okay, so for example, if we want to derive P of CK, we just marginalizing it over X and then derive P of CK, or you could conditioning that based on CK and derive this term. So this is a more informative distribution, as we mentioned that, but we don't need that in all of the situations. Sometimes it just, this is enough for us to make a decision. So now our goal is to minimize the chance of assigning X to the wrong class. Then in fact we would choose the class having the higher posterior probability, right? So we want to minimizing the misclassification rate. Okay, we need, in fact, we need a rule that assigns each value of X to one of the available classes. such value will divide the input space into let's say RK regions. The regions don't need to be contiguous, but okay, to clear that, suppose we have just two classes as our example. We had two classes that somebody is normal or has cancer. The probability of making mistake is somebody is in region 1. When X is in region 1, we decide to actually call that person as cancer. Okay, so the probability of making mistake is somebody we predict somebody has cancer, although the R1 is actually the region that somebody is normal. So we predict somebody is normal, but he has actually cancer. C2 means that he has cancer, and plus the probability of somebody image is in region 2, so we decide to tell him he has cancer, but he is normal, so it is C1. Okay, so it is equal to the just integration over distribution, and this is the probability of making mistake. Maybe it is better to show that in one image. So if this is X and let's say this is the joint probability of X and C1, and this is the probability, the joint probability of X and C2, and let's say we call this X hat, which is our threshold, and actually this specify the decision boundary. So whatever is before that, we assign that to R1 for means that it is in the region 1. In other words, means that for us it means that somebody is normal, so it doesn't need to take a treatment for him or her, and this is the region 2 for us, means that we decide to take a treatment for that person. So what is our what is the probability of making mistake is actually somebody, it is in this region, means that it is in the joint probability of X and C2, but we decided to be in the region of R1. So as you could see, this is the first integration, and the second term is here. Okay, this is the second error area, which is belong to the joint probability of X and C1, but we decide that it is in the region 2, which is incorrect, because region 2 means that somebody has cancer, but we know that this joint probability belongs to somebody is normal. Okay, and for deciding, just note that we can write the P of X and C2. In general, it could be CK is equal to CK given X times P of X. And so this is just using of product rule in here. And we know that P of X is common in both of these. So the P of, we could rewrite that in this way. Okay, the P of mistake is equal to integration over region 1 P of C2 dx plus integration over region 2 P of C1 given X times P of X. And the P of X is equal for both of them. So if we want to assign X to one class, we just need to determine the P of CK times X. So if, in this case, if the P of C1 given X is greater than P of C2 given X, means that we decide that that person is normal. And if P of C2 over X given X is greater than P of C1 given X, means that somebody has cancer. So, and this is the decision rule for us. Okay, so we just need to calculate the conditional probability in here. But this maybe has some problem. Maybe we could do some improvement in this. What is the problem with this? In the cancer example that we talked about it, if somebody has cancer but we classify him or her as somebody who is normal, then it is so dangerous and it is so worse than somebody is normal but we just classify him or her as somebody has cancer. Because in the second case, just that person goes for further investigations and this kind of stuff. But in the first case, the person probably dies because of our mistake. So the weights of making mistake is not the same in general for different regions. Thus, in general, we can formalize it with introducing a loss matrix, loss function matrix, or relative loss matrix. Let's say we have X, which is our input, and its corresponding class is CK, but we assign Cj to that input. We could form a loss matrix as, for our example, which is a 2D example, as follows. It is 0. It is just an example. And this is for normal. Or if, let's say, this is normal, cancer, okay, just show that with cancer, normal, cancer, and normal. Okay, in this case, we show that with L, and this means that, and this is the loss matrix, means that if somebody has cancer and we predict that that person has cancer, so the relative loss is 0. If somebody has cancer but we predict that he is normal, its relative loss is 1000 in comparison with the opposite case, that somebody is normal but we predict that he has cancer. Okay, in other words, if somebody is normal but we predict that he has cancer, is better than somebody has cancer but we predict that he is normal. Okay, so this is 1000 times worse than this case for us. So in this case, we want to minimize our loss function and find the optimal solution. So we want to minimize the loss, but because we don't know the true labels, because this has some uncertainty and this kind of things in the labels, we minimize the expected loss. So we could write that as sum over k, sum over j, integration over region rj, l kj, and the lkj is the elements of this matrix. So it is lkj times the joint probability of x and ck times t of x. So we want to minimize this. And now if we want to decide, if we have an x and we want to decide which class x belongs to, we just need to calculate this value, joint probability of ck, or in other words, we just need to compare the value of ck given x. In this case, for different value of j, we could compare this value and assign x to that class. For example, in our class, in our example, which has two classes, we have for the class of normal person, if we call the class of normal person class 1, it is C1. We should first calculate this, then calculate this for cancer, then just compare these two. Then based on this is greater than this or this is greater than this, just decide who has that person has cancer or is normal, and the minimum of these two is the winner. Okay. Okay, so we have broken classification problems into two different stages. The first one is the inference stage, in which we obtain conditional probability of ck given x, and the second stage is decision stage, which we will use the decision theory to assign a class to x, okay, or a class assignment. Okay, but actually we have another solution for solving our problem. As an alternative solution is to solve both of these problems at the same time and learn a function that can map the x directly into the labels. We call this discriminant function. In fact, if you want to put them in a nutshell, we have three different approaches, and now we list them in decreasing order of complexity. So the first approach to solve our problem is to solve inference problem by obtaining class conditional probability, which is p of x given ck, and deriving p of ck, then using Bayes' theorem to derive this probability of ck given x using Bayes' theorem, and we know that we can expand this term as p of x given ck times p of ck. So after obtaining this, we can use the decision theory. So after that, we could use decision theory for assigning a class to the variable x. So in this approach, we model our distributions. So we call these approaches generative models. Why generative models? Because after modeling our distributions, we could sample from them and generate new data from them. For example, let's say the x's are some face images, and and the C1 is, let's say, woman face, and the C2 is man face. Now, if we obtain P of the conditional probability of X given C1, by sampling from this, we could generate woman faces, okay? Or by sampling from this distribution, we could generate man face. Or in general, with sampling from this distribution, we could generate faces, okay? So we call this approach as generative models. The next possibility is to directly derive the conditional probability of CK given X, then using decision theory to assign class to X. We call this approach and models that model the posterior probability directly discriminative models. And the next approach is to find a function that maps X directly onto a class label. And in this case, probabilities play no role. So, for example, in binary case, we have a function, we derive a function f of x. If f is equal to 0 means that we have the class 1, and if f of x is equal to 1, we know that our class is C2. So, okay, how should we compare these three approaches? Okay, in the first approach that we obtained class conditional probabilities, usually X has very high dimension. Like images, we have lots of pixels, so we have very high dimension for X, so we need very large training data. But on the other hand, we know that we can calculate P of X, which is very useful when we want to detect some new data that has low probability. Other approaches can give very low accuracy or can fail, but in this approach, because we know what is the probability of what is the distribution probability of X, so we can use that to detect that for new data that are hard for other approaches. We call this outlier detection. And this is one advantage of this way, but generally these generative models are computationally very expensive and they are hard to train typically. The next one is the approaches of the second approach. Is we just want to use decision theory, so the posterior probability is enough for us, because in the previous approaches we obtain all of the probabilities which make these approaches hard, but for making decision we just need to know the posterior probability. So these approaches are easier than the approaches in comparison with the first approaches. And the third one is the mapping the X directly onto a label. The major problem of this approach is we no longer access to the probabilities. This is very major disadvantage for different reasons that you could refer to the textbook to know about them. We want to access to the posterior probability at least, but in the last methods which we obtain a function that directly map X into the output label, we do not have access to the probabilities or posterior probabilities, which is a major drawback of these approaches. Okay, now as finishing example, we want to talk about the loss function for regression. In the continuous, because our example was about the cancer, was a classification problem, in that the decision was being the class 1 or class 2. But in the regression, our decision is actually is an estimation problem. So we have the actual y of the given x, and we could define as we defined a matrix in the classification problem. In here also we could define a loss function for the target values and the model output. Actually, this is the model output and this is the actual value. So the expected loss is the integration of our loss function times the joint probability of x and t. So this is the expected loss, and it is very common to use a squared loss as the loss function. So we could choose the loss function as y of x minus t squared. So if we plug this loss into the expected loss function, it would be the integration of y of x minus t squared, the joint probability dx dt. So we want to minimize that with changing the y of x. For minimizing this, actually you need to use calculus of variation, which is similar. In this case it is similar to the taking the derivative, but in general concept, it is different from the derivative, because when you taking a derivative of function, you just want to know the change of the function in just one particular point, but in here you want to know the change of expected loss regarding to different function of y of x. So these are slightly different, but we don't want to, you don't need to know much about it. Okay, so we could write this we could set this as 0 and derive the estimation of y of x, the model output that can minimize this loss function, and that is the integration of t joint probability over p of x. And we know that the joint probability over this is the conditional probability of t given x, that is dt, and actually this is the expected value regarding to t given x. Okay, so this means that the best value of x is the conditional average of t on x. So we call this regression function. So now, because we have this, maybe it is better to derive this from another way. It could be intuitive to if we write the y of x minus t squared in this way, we just add and subtract expected value of conditional probability if you write the squared loss in this form, we just subtract and add a term and you expand it. So you could write the expected loss as the integration of y of x minus the conditional expected value squared p of x dx plus the integration expected value of t given x minus t squared px dx. And if you want to minimize this with respect to y of x, this term has nothing to do with y of x, so you just need to making y of x equal to expected value of t of x. So we knew that from the previous method that we derived this, but something that is interesting is the second term. The second term is actually, we could see that as the variance of the distribution t average over x, and it is some kind of noise, and as we could see, we could not reduce that with changing of y of x, and because it is independent of y of x, it is irreducible. So in this session, actually this was the end of this session. and I hope that you gained some intuition about the decision theory and why we learned about probability theory. Now you should know actually what was the reason that you learned about the probability theory, and in the next session we probably talk about information theory, that it is very useful to analyze the problem and dive into machine learning much more. I hope you enjoyed from this session. Hope to see you in the next session. Bye.